Okay, what I have here is a model that contains 4 variables, and that has been analyzed using data from several school districts. The variables are years of average teacher experience in each school district, number of in-school suspensions, and number of out-of-school suspensions. These are the 3 predictor variables. And the criterion variable, or the main dependent variable here, is SAT scores. This analysis employs an algorithm that allows one to identify and take into consideration noncyclical nonlinear relationships, which are relationships such as log, exponential decay, as well as quadratic relationships. And in order to do this analysis, I changed the settings to WarpPLS regression. The PLS regression algorithm would have done the analysis linearly. Robust path analysis also would have done the analysis linearly, but with a simpler algorithm. So I used this particular one here, WarpPLS regression. And I obtained these results here. So my results are that in-school suspensions has a non-significant effect on SAT scores, but years of teaching experience has a significant effect on SAT scores, indicated by the p-value lower than 0.05, and out-of-school suspensions also have a significant effect on SAT scores, indicated by the low p-value. However, before I accept these findings, I have to look for a couple of possible problems here. One is too high collinearity among these variables. So let me see. Let me go to this view latent variable coefficients table, and let me look at these focal linearity VIFs. Typically, the VIFs that I'm looking for here, if I have only latent variables, that is, only variables that are aggregates of other variables, I would look for focal linearity VIFs that are lower than 2.5 ideally, and no greater than 3.3. For models that contain variables that are not latent variables, that are measured through one single indicator, or one single column in a data set, then I'm looking at focal linearity VIFs that are ideally lower than 5 and no greater than 10. And I have all of the focal linearity VIFs lower than 5 here, so I can assume that that collinearity is not a big problem here. However, there are some signs of problems, and they are indicated by a negative r squared and a negative q squared. Typically, these should be positive. So that's a red flag, and that suggests that there may be a problem of Simpson's paradox in my data set, in that I may have one or more predictors here that are making a negative contribution to the r squared in this criterion variable. The r squared is the percentage of explained variance in the criterion variable, and this is indicated by a different sign between the path coefficients and the correlations among the latent variables. So let me take a look at the correlations among latent variables. So here I have them. So I'll resize this window a little bit, and this one too, so that I can have them side by side. And now look for instances where the path coefficient and the correlation coefficient have different signs. So let's say this one here, it's positive path coefficient. Let's look at the corresponding correlation coefficient. It's also positive. This one, in-school suspensions SAT, we have a negative correlation, and the correlation, I'm sorry, the path coefficient is negative, the correlation is also negative. And for out-of-school suspensions, I have a path coefficient that is positive, but the corresponding correlation is negative. So here I have an instance of Simpson's paradox, which tells me that one or two things are happening here. One of the things that may be happening is that this link is reversed. The other is that this link does not belong here. So what I'll do is I will assume that this link doesn't belong here, and this is non-significant. So I will basically, what I'll do is to change this model and redo the analysis with these two variables removed, and I'll see what I have as results later on. So now I have the same model with those variables removed, and I can see here that the path coefficient and the correlation associated with that path coefficient, which should be the same, by the way, they have both the same sign. So this nonlinear analysis essentially tells me that the relationship is quasi-linear, and that for each one standard deviation variation in years of teacher experience, I have an increase of 0.24 standard deviations in SAT scores. So while initially a nonlinear analysis might have looked like it was providing results that were different from the results obtained through a linear analysis, in fact it did not provide new results, because the results, they were biased by the Simpson paradox phenomenon, which is a situation where I have a path coefficient and a correlation coefficient that are of different signs, so one or more of those situations, and that required me to redo the analysis without two of the variables, without one of the variables. The other I removed because its effect on SAT score was non-significant. So what I ended up getting was very similar to the results that I would have gotten through a nonlinear analysis.